You might think air conditioning was invented in the 20th century, but the Romans were chilling their homes with water-powered cooling systems over 2,000 years ago. While we're cranking up electric units and paying massive energy bills, these ancient engineers figured out how to turn stone walls into natural refrigerators using nothing but flowing water and clever physics. Picture this. It's 100 degrees Fahrenheit in ancient Rome. The sun is beating down like an angry god, and you're wearing a toga that's basically a bedsheet wrapped around your body. Not exactly the ideal outfit for a heatwave, but step inside a wealthy Roman's villa and suddenly you're hit with a cool breeze that feels like magic. The walls themselves are somehow cold to the touch, and the air carries a refreshing mist that makes you forget you're in the middle of a Mediterranean scorcher. What you're experiencing isn't magic. It's engineering brilliance that would make modern architects weep with envy. The Romans didn't just build houses. They built climate-controlled environments using techniques so advanced that we're still trying to figure out exactly how they pulled it off. These weren't simple fountains or decorative water features we're talking about. This was full-scale atmospheric manipulation hidden behind beautiful marble facades. The genius started with something Romans called spicus aquarum, literally meaning water channels. But these weren't your typical plumbing pipes. We're talking about intricate networks of stone conduits built directly into the walls themselves, creating a circulatory system that would make a cardiologist jealous. Imagine if your house had blood vessels, except instead of blood, cool water flowed through every wall, ceiling, and floor. Here's where it gets really interesting. Roman engineers understood something that took us centuries to rediscover. Water doesn't just cool things when it's cold, it actively absorbs heat as it flows. They built these hidden channels at specific angles and depths, calculating the exact flow rate needed to pull heat out of rooms faster than the sun could pump it in. It's like having a liquid heat vacuum cleaner running through your walls 24 hours a day. But the Romans didn't stop at basic heat absorption. They figured out how to turn evaporation into air conditioning. By letting water seep through specially designed porous stones, they created controlled evaporation zones that cooled the air while adding just enough moisture to make breathing comfortable. The water would slowly weep through the stone surfaces, creating microscopic cooling zones that dropped room temperatures by up to 20 degrees. The scale of these systems was absolutely mind-blowing. A typical wealthy Roman villa might have over 2,000 feet of water channels running through its walls. That's nearly half a mile of hidden plumbing designed purely for climate control. The water would enter the system from elevated aqueducts, flow through the cooling network, and eventually drain into gardens or decorative pools, creating a continuous cycle that never wasted a drop. What made this even more impressive was how they disguised the whole operation. From the outside, these looked like normal stone walls decorated with beautiful frescoes and mosaics. But hidden behind that artistic facade was a sophisticated cooling network that would make modern HVAC engineers scratch their heads in amazement. The Romans basically invented invisible air conditioning using nothing but stone, water, and pure ingenuity. The engineering challenges were enormous. Water pressure had to be perfectly balanced to ensure even flow throughout the entire system. Too much pressure, and the channels would burst. Too little, and the cooling effect would fail. Roman engineers developed pressure-regulating chambers and flow control mechanisms that automatically adjusted water distribution based on temperature changes and seasonal demand. They even figured out how to create different climate zones within the same building. The dining room might be kept slightly warmer for comfort during meals, while the sleeping quarters were maintained at cooler temperatures for better rest. Each zone had its own network of channels with individually controlled flow rates. It's like having a smart thermostat system, except it was carved out of stone by guys wearing sandals. The most clever part of the whole system was how they dealt with the water supply. Romans didn't just pump water through their walls and call it a day. They created recycling systems that would make modern environmentalists weep with joy. Water would flow through the cooling channels, absorb heat from the rooms, then get directed to special cooling chambers where it would be chilled before being recirculated back through the system. These cooling chambers were architectural marvels in themselves. Built underground or in shaded areas, they featured large stone basins where heated water would pool and cool naturally through evaporation and contact with cool stone surfaces. Some of the more elaborate systems even included ice chambers, specially designed rooms where snow and ice collected during winter could be stored and used to supercool the water during summer months. The Romans understood thermal dynamics in ways that seem almost supernatural. They knew that moving air felt cooler than still air, so they designed their water walls to create gentle air currents. As water evaporated from the stone surfaces, it created convection currents that moved cool air through rooms while pushing hot air out through carefully positioned ventilation openings. But here's what really blows your mind. They figured out how to make their cooling systems work better during the hottest parts of the day. By positioning water channels on the sunny sides of buildings, they created temperature differentials that actually increased the cooling effect when it was needed most. The hotter it got outside, the more efficiently their system worked. Talk about turning a problem into a solution. The water walls weren't just functional, they were beautiful. Romans integrated decorative elements like small waterfalls, gentle fountains, and even musical water features into their cooling systems. Imagine relaxing in a cool room where the walls themselves were quietly gurgling with flowing water, creating both comfort and ambience. It was like living inside a natural spa that happened to be your house. Different regions developed their own variations of the water wall concept. In the hot, dry climate of North Africa, Roman engineers created systems that maximized evaporative cooling. In the more humid areas around the Mediterranean, they focused on heat absorption techniques. Each system was custom designed for its local climate, proving that Romans understood regional weather patterns better than most modern meteorologists. The construction process was incredibly complex. Builders had to plan the entire water network before laying the first stone, creating detailed blueprints that showed every channel, junction, and flow control point. The walls had to be built with precise tolerances to ensure the water channels were perfectly sealed, while still allowing controlled evaporation where needed. Roman engineers even developed quality control systems to test their cooling networks. They would fill the channels with colored water to check for leaks, measure flow rates at different points in the system, and test temperature differentials to ensure optimal cooling performance. If a section wasn't working properly, they could isolate it and make repairs without shutting down the entire system. The social impact of these cooling systems was enormous. Wealthy Romans could host elaborate dinner parties during the hottest summer days, impressing their guests with comfortable temperatures while everyone else was sweating buckets. It became a symbol of status and engineering sophistication that separated the elite from the ordinary citizens. But the technology wasn't limited to private homes. Public buildings, bathhouses, and government facilities all incorporated water wall cooling systems. Some of the largest installations could cool spaces big enough to hold hundreds of people, creating comfortable environments for civic gatherings and commercial activities even during brutal heat waves. The maintenance of these systems required specialized knowledge and skilled technicians. Romans developed a whole profession around water wall maintenance, with experts who understood hydraulic pressure, stone preservation, and thermal dynamics. These technicians were so valued that they often received special privileges and high pay for keeping the cooling systems running smoothly. What's truly remarkable is how these ancient engineers solved problems that we're still struggling with today. How to cool buildings efficiently, how to minimize energy consumption, and how to create comfortable living spaces without destroying the environment. They did it all using renewable water power and natural materials, creating sustainable cooling systems that could run indefinitely without any external energy source. The most ingenious part of Roman water wall technology was how they solved the seasonal challenge. During winter months, when cooling wasn't needed, these same systems could be converted into heating networks. By redirecting hot water from hypocaust furnaces through the wall channels, Romans created radiant heating that warmed rooms evenly from within the walls themselves. It's like having a reversible climate control system that worked year-round, switching from air conditioning in summer to central heating in winter with just a few valve adjustments. But here's where things get really wild. Roman engineers figured out how to create what we'd now call smart home automation, using nothing but water pressure and gravity. They developed automatic temperature control systems that adjusted water flow based on ambient conditions. When rooms got too hot, increased evaporation would trigger pressure changes that opened more water channels. When temperatures dropped, the system would automatically reduce flow to maintain optimal comfort levels. The physics behind this automation was brilliant. Romans used thermal expansion principles to create mechanical switches carved from bronze and stone. As water heated up, metal components would expand and trigger valve mechanisms that increased cooling flow. When temperatures cooled down, the metals would contract and reduce water circulation. These ancient thermostats were so sensitive, they could detect temperature changes of just a few degrees and respond automatically. Some of the more elaborate installations included what Romans called refrigeraria, specialized cooling chambers that could actually create ice during winter for summer storage. These underground facilities featured thick stone walls filled with water channels that would freeze solid during cold months. The ice would then be harvested and stored in insulated chambers, ready to supercool the water wall systems during scorching summer heat waves. The construction techniques for these ice storage systems were absolutely mind-boggling. Roman engineers would build layered stone chambers with air gaps for insulation, similar to modern thermos bottles but scaled up to room size. They lined these chambers with lead sheets to prevent water infiltration and covered everything with thick layers of straw and wool for additional insulation. Some of these ice storage facilities could preserve frozen water for up to 6 months in Mediterranean climates. Water quality was another massive engineering challenge that Romans tackled head-on. They couldn't just pump any old water through their precious cooling systems without risking blockages from sediment or mineral buildup. So they developed filtration networks that would make modern water treatment plants look simple by comparison. Multi-stage filtration systems using sand, charcoal, and specially treated stones removed impurities before water entered the cooling channels. The filtration process was integrated right into the water wall design. As water flowed from aqueducts into villa cooling systems, it would pass through settling chambers where heavy particles dropped out, then through layers of filtering materials that caught smaller contaminants. Some installations even included biological filtration, using carefully selected aquatic plants that absorbed minerals while adding oxygen to the water. Roman engineers understood that stagnant water was a recipe for disaster. They designed their systems with continuous flow patterns that prevented water from sitting still long enough to develop algae or bacterial growth. Every channel had multiple entry and exit points, creating circulation patterns that kept water moving constantly throughout the entire network. It was like having a circulatory system that never stopped pumping fresh, clean coolant through every wall in the building. The social engineering aspect of these cooling systems was just as impressive as the technical achievements. Wealthy Roman families would compete to see who could create the most comfortable and innovative cooling environments. Some villas featured cooling systems so advanced they could maintain different temperatures in different rooms simultaneously, allowing family members to customize their personal comfort zones. One particularly extravagant installation reportedly included scented cooling systems, where aromatic herbs and flowers were placed in strategic locations within the water channels. As air flowed over the water-cooled surfaces, it would pick up pleasant fragrances and carry them throughout the house. Imagine having air conditioning that not only cooled your home, but also made it smell like a Mediterranean garden. The military applications of water wall technology were equally fascinating. Roman commanders figured out that comfortable troops were more effective troops, so they incorporated cooling systems into military installations across the empire. Fort cooling systems had to be more robust and simpler to maintain than civilian installations, leading to innovations in modular design and quick repair techniques. These military cooling systems could be rapidly deployed and assembled using standardized stone components. Roman engineers developed prefabricated channel sections that could be transported and assembled at new locations, like ancient IKEA furniture, but designed to cool entire buildings. Legion engineers became experts at surveying local water sources and designing custom cooling networks that could be built quickly using local materials and labor. The economic impact of widespread cooling technology was enormous. Regions with advanced water wall systems could maintain productive activities during summer months when other areas ground to a halt due to extreme heat. This gave Roman territories with sophisticated cooling infrastructure significant economic advantages, contributing to the empire's prosperity and technological dominance. Trade networks developed around cooling system components and expertise. Specialized stone carvers who could create precise water channels commanded premium prices. Engineers with cooling system design experience were recruited across the empire to build installations in new territories. Even the maintenance and repair of existing systems created entire economic sectors that employed thousands of skilled workers. Roman cooling technology influenced architecture across the known world. As Roman influence spread, local builders began incorporating water wall principles into their own construction projects. This led to fascinating hybrid designs that combined Roman hydraulic engineering with local architectural traditions and climate conditions. Different cultures adapted the basic water wall concept to their own needs and materials. In desert regions, builders focused on maximizing evaporation effects to combat dry heat. In more humid areas, the emphasis was on heat absorption and air circulation. Some cultures even developed portable cooling systems that could be moved seasonally or transported during nomadic migrations. The decline of Roman cooling technology wasn't sudden. It was a gradual loss of knowledge and expertise as the empire fragmented. Maintaining these complex systems required specialized skills that were passed down through generations of engineers and technicians. When political instability disrupted these knowledge networks, the sophisticated cooling systems gradually fell into disrepair and were eventually abandoned. Many of the techniques were simply forgotten until modern archaeologists began uncovering the remains of these ancient climate control systems. What they found challenged everything we thought we knew about Roman technological capabilities. These weren't primitive attempts at cooling. They were sophisticated engineering solutions that in some ways surpassed modern approaches to sustainable climate control. The rediscovery of Roman water wall technology is inspiring modern architects and engineers to rethink how we approach building climate control. Some contemporary projects are incorporating updated versions of Roman cooling principles, using modern materials and precision engineering to create energy-efficient cooling systems that work on the same basic principles the Romans mastered 2 millennia ago. The most mind-blowing discovery came when archaeologists realized that Romans weren't just cooling individual rooms. They were creating entire microclimates within their buildings. Some of the larger villas had cooling zones that extended beyond the walls themselves, creating cool air pockets in courtyards and garden areas. They basically figured out how to air condition outdoor spaces using nothing but strategically placed water channels and clever airflow design. Here's where Roman engineering gets absolutely crazy. They developed what we'd now call zoned climate control centuries before anyone even dreamed of programmable thermostats. Different areas of a villa could be maintained at completely different temperatures depending on their intended use. The kitchen area might be kept slightly warmer to help with food preparation, while the library was kept cool and dry to preserve scrolls and documents. Storage areas for wine and food had their own specialized temperature ranges, all controlled by the same integrated water wall network. The precision required for this multi-zone cooling was staggering. Roman engineers had to calculate water flow rates, channel dimensions, and evaporation zones for each area independently, while ensuring the entire system worked together harmoniously. One miscalculation could throw off the temperature balance for the whole building. It's like conducting an orchestra where every instrument is a different water channel, and they all have to play in perfect harmony to create comfortable temperatures. But wait, it gets even more impressive. Some Roman installations included what modern engineers would recognize as heat exchangers, devices that transferred heat from hot water to cool water without mixing the two streams. These ancient heat exchangers used coiled stone channels where hot water from sun-heated roof collectors would flow past cool water from underground sources, transferring heat while keeping the water supplies separate. The construction of these heat exchangers required stone carving skills that bordered on artistic genius. Craftsmen had to create perfectly smooth, curved channels with precise dimensions to ensure optimal heat transfer. The stone surfaces had to be polished to reduce friction and prevent mineral buildup that could clog the system. Some of these carved heat exchangers were so beautiful, they doubled as decorative architectural elements. Romans even figured out how to use solar energy to power their cooling systems more efficiently. They installed dark stone collectors on rooftops that would absorb solar heat during the day, warming water that would then be directed through underground cooling chambers at night. This created a thermal battery effect where daytime heat was stored and released after sunset, maintaining comfortable temperatures around the clock. The night cooling technique was particularly clever because it took advantage of the natural temperature drop that occurs after dark. As the solar-heated water released its stored energy into the cooling chambers, it would chill rapidly in the cooler night air. By morning, this supercooled water would be ready to provide maximum cooling effect during the hottest part of the next day. Quality control for these complex systems required testing methods that would impress modern engineers. Roman technicians developed water-based measuring devices that could detect temperature differences as small as 2 degrees. They used colored dyes to trace water flow patterns through the hidden channels, ensuring even distribution and identifying potential blockage points before they became problems. The testing process included seasonal calibration procedures, where technicians would adjust flow rates and pressure settings based on changing weather conditions. Spring testing focused on preparing systems for summer heat loads, while autumn inspections prepared the networks for winter shutdown or heating mode conversion. These maintenance schedules were so detailed they included specific dates for different types of inspections and repairs. Roman engineers understood that their cooling systems needed to handle emergency situations too. They built bypass channels and emergency drainage systems that could quickly remove water from the walls if repairs were needed. Some installations included emergency cooling protocols that could rapidly drop room temperatures during heat waves or medical emergencies when patients needed immediate temperature relief. The emergency systems featured manually operated valves that could flood cooling channels with ice-cold water from underground storage chambers. These crisis cooling protocols could drop room temperatures by 30 degrees in less than an hour, creating life-saving relief during medical emergencies or extreme weather events. It was like having an emergency room climate control system built into your house. Water source management was another engineering marvel that Romans perfected for their cooling systems. They couldn't rely on a single water supply for such critical infrastructure, so they developed redundant supply networks with multiple aqueduct connections and backup storage systems. If one water source failed, the cooling system could automatically switch to alternative supplies without interrupting operation. The backup water systems included elevated storage tanks that could gravity feed the cooling networks during supply disruptions. These emergency reservoirs were strategically positioned to provide several days of cooling capacity, even if all external water sources were cut off. Some wealthy Romans maintained private water reserves that could keep their cooling systems running for weeks during sieges or natural disasters. Romans also developed water recycling techniques that would make modern environmental engineers jealous. Used cooling water wasn't just dumped, it was directed through settlement ponds where sediments could be removed, then through biological filtration systems using aquatic plants before being reintroduced into the cooling network. This closed-loop system could operate almost indefinitely with minimal water waste. The recycling process included water quality monitoring using taste tests and visual inspections that could detect contamination before it affected the cooling system's performance. Trained technicians could identify mineral buildup, biological growth, or chemical changes that might damage the stone channels or reduce cooling efficiency. These ancient water quality specialists were essentially the first HVAC maintenance crews in human history. Different regions of the Roman Empire developed specialized cooling techniques adapted to local climate conditions and available materials. In volcanic regions like around Mount Vesuvius, engineers incorporated natural geothermal cooling, using underground springs that stayed naturally chilled year-round. These geothermal systems could provide cooling without any external energy input, creating perpetual air conditioning powered by the Earth itself. Desert installations focused on maximizing evaporative cooling effects using specially designed stone surfaces that increased water contact with dry air. These systems could create comfortable indoor environments even when outside temperatures exceeded 120 degrees Fahrenheit. The evaporative cooling chambers featured intricate stone latticeworks that maximized surface area while maintaining structural integrity. Coastal installations took advantage of sea breezes and ocean temperature differentials to enhance their cooling systems. Romans built specialized intake channels that could draw cool air from over the water and direct it through their building cooling networks. These maritime cooling systems combined natural ventilation with water wall technology to create incredibly efficient climate control. The coastal systems included tide-powered water circulation mechanisms that used rising and falling sea levels to automatically pump fresh seawater through cooling chambers. As tides changed, different chambers would fill and empty, creating continuous water circulation without requiring any manual pumping or external energy sources. It was like having a tidal-powered air conditioning system. Mountain installations incorporated snowmelt and high-altitude cooling techniques that could maintain comfortable temperatures even during summer heat waves. These alpine cooling systems used gravity-fed networks that brought glacial meltwater down from mountain peaks through insulated channels that preserved the water's natural chill. The mountain systems featured sophisticated flow control mechanisms that could regulate water temperature by mixing streams from different elevations. Warmer water from lower slopes could be blended with ice-cold mountain streams to achieve precise temperature control throughout the cooling network. These altitude-based climate control systems were like having a natural refrigeration plant built into the mountainside. Urban installations had to deal with space constraints and noise considerations that didn't affect rural villas. Romans developed compact cooling systems that could fit within the confines of city buildings while maintaining effective temperature control. These urban systems often featured shared cooling networks that served multiple buildings, creating neighborhood-scale climate control infrastructure. The shared urban cooling systems required sophisticated coordination between property owners and municipal water authorities. Romans developed legal frameworks and maintenance agreements that governed how shared cooling infrastructure would be funded, maintained, and operated. These ancient cooling cooperatives were essentially the first utility companies dedicated to climate control services. Industrial applications of water wall cooling technology helped Romans maintain productivity in manufacturing and food processing operations during extreme heat. Blacksmith shops used cooling walls to maintain tolerable working conditions near their forges, while food storage facilities used the technology to prevent spoilage during summer months. Even public bakeries incorporated cooling systems to keep working conditions bearable for bakers during bread production. The industrial cooling systems had to be more robust and heat-resistant than residential installations. They used thicker stone walls, higher water flow rates, and specialized heat-resistant materials that could handle the extreme temperatures generated by industrial processes. Some installations included emergency cooling protocols that could rapidly reduce temperatures if working conditions became dangerous. Religious and ceremonial buildings featured cooling systems designed to maintain comfortable conditions during large gatherings and important ceremonies. Temple cooling networks had to handle the heat generated by crowds of worshippers while maintaining the dignified atmosphere appropriate for religious observances. These systems often incorporated decorative water features that enhanced both cooling effectiveness and spiritual ambiance. The ceremonial cooling systems included special chambers where priests and important officials could retreat to cooler areas during long ceremonies. These climate-controlled sanctuaries featured enhanced cooling capacity and luxurious appointments that reflected the high status of their occupants. It was like having VIP climate control within already sophisticated temple cooling networks. Medical facilities incorporated cooling technology specifically designed to aid patient recovery and maintain sanitary conditions. Roman hospitals used cooling systems to prevent infection, reduce fever symptoms, and create comfortable environments for healing. The medical cooling networks featured adjustable temperature zones that could be customized based on different types of treatments and patient needs. Hospital cooling systems included specialized chambers for treating heat-related illnesses and fever management. These medical climate control facilities could rapidly reduce patient body temperatures through controlled exposure to precisely cooled air and water vapor. Roman military medics became experts at using cooling technology to treat battlefield injuries and heat exhaustion among troops. The legacy of Roman water wall technology extends far beyond ancient history. Modern sustainable building designers are rediscovering these principles and adapting them for contemporary climate control challenges. Some cutting-edge green buildings now incorporate updated versions of Roman cooling techniques, proving that these ancient innovations remain relevant for modern environmental and energy challenges. Contemporary architects studying Roman ruins have discovered cooling installations that challenge everything we thought we knew about ancient construction capabilities. Some of these systems were so sophisticated that modern engineers initially dismissed them as impossible until computer modeling proved the Romans had actually achieved thermal efficiency rates that rival today's best HVAC systems. The most shocking discovery came from a villa excavation near Pompeii, where archaeologists found evidence of what can only be described as ancient air conditioning ducts. These weren't simple water channels. They were carefully engineered air circulation networks that used water-cooled surfaces to create controlled air currents throughout entire buildings. The stone ductwork was so precisely carved that air flowed through it with minimal resistance, creating gentle breezes that felt like natural wind but were actually manufactured comfort. These air circulation systems worked by creating pressure differentials using water temperature variations. As water evaporated from cooling surfaces, it created low-pressure zones that drew fresh air through intake channels while pushing stale, warm air out through strategically placed exhaust openings. It's like having a whole house fan system powered entirely by evaporation physics. But here's where Roman engineering reaches absolutely mind-bending levels. They figured out how to create what modern meteorologists would recognize as artificial weather patterns inside their buildings. By carefully controlling humidity levels and air movement, they could generate indoor rain showers, morning mist effects, and even simulate the feeling of being near a mountain stream, all while maintaining perfect temperature control. The artificial weather systems used precisely calculated water release rates through microscopic pores in specially prepared stones. These climate chambers could produce everything from gentle humidity that felt like a spring morning to dramatic cooling mists that dropped temperatures instantly during heat emergencies. Some wealthy Romans literally lived inside their own personal weather systems. The stone preparation for these microclimate chambers was an art form that required years of training. Craftsmen would select specific types of limestone and marble based on their porosity characteristics, then treat them with natural compounds that controlled exactly how much water could seep through. Different stones produced different atmospheric effects, allowing Romans to customize their indoor weather based on personal preferences. Quality control for artificial weather systems involved teams of specialists who could predict exactly how different stone treatments would behave under various temperature and humidity conditions. These ancient climate engineers developed testing protocols that could simulate seasonal weather changes and adjust their systems accordingly. They basically created the world's first climate laboratories, using nothing but stone, water, and centuries of accumulated knowledge. The most elaborate installations featured what Romans called tempestas domestica, domestic storm systems that could create cooling thunderstorm effects without the lightning or actual rain. These controlled storm chambers used rapid temperature changes and air pressure manipulation to generate the refreshing feeling of an approaching thunderstorm, complete with the electrical charge that makes the air feel crisp and clean. So the next time you're sweating through another scorching summer day, while your electric bill climbs higher than a gladiator's sword, remember the Romans who figured out how to chill their homes, using nothing but water, stone, and pure engineering genius. They built climate control systems so advanced that we're still trying to catch up 2,000 years later. Makes you wonder what other brilliant solutions are hiding in ancient ruins, just waiting to revolutionize our modern world.